Hi, I'm Mr. Young, and in this podcast, I'd like to coach you through the chemistry of life and the importance of carbon. To begin, what do each of the following molecules have in common? All right, now I'll give it to you. You're right, they're all gases. But more importantly, these four key gases are thought by many scientists to have been those that comprise the early atmosphere of Earth. Simple compounds, very few atoms. But these molecules are at the core of a hallmark piece of research that's cited in textbooks worldwide and that is used by many scientists to suggest that life may have in fact come from non-living matter at one point in time, or to support, in other words, the idea of abiogenesis or spontaneous generation. You see, in 1953, Stanley Miller, a graduate student at the University of Chicago, created this apparatus to try to simulate the early Earth in an attempt to evaluate this abiogenesis thought. In other words, can we take non-living matter and have coming from non-living matter life? In other words, abiogenesis or spontaneous generation. To try to evaluate this and to test it, he took this flask and filled it with essentially primordial soup or ocean-like matter, water, and exposed it to a heat source to simulate the geothermal activity of the early Earth that was thought to have been present. Of course, as the water evaporated, it went through this tubing that's shown here, and then into the atmospheric chamber, a chamber to simulate the early atmosphere. And inside, you can see the exact same four gases that we identified earlier: water vapor, methane, ammonia, hydrogen gas. Well, it was also thought that the early Earth's atmosphere had a lot of electrical charges involved, a lot of electricity in the form of lightning. And to simulate that, Miller took electrodes and had a spark going between them. And the whole idea was, could we somehow rearrange the atoms that are found in those different chemicals in the gases to form something more complex than the simple inorganics and the very simple organic compound of methane? Well, after this part of the apparatus, then the gas would come through a condenser and would condense. The condensate would then collect down here below, and Miller would be able to extract the condensate to analyze what was in it. But what did he find? Aren't you dying to know? What he found were some trace amino acids, the building blocks of proteins, one of the major macromolecules that builds life. No, he didn't find living things, didn't find any cells. He found some basic organic compounds. And what are organic compounds? Well, that brings us back to the periodic table. Organic compounds used to be thought as only those compounds that can be created within living things, found within living things. But that was kind of revised after we discovered that in the lab we could synthesize some organic compounds. What we recognize organic compounds today to be are those compounds that really contain carbon. Carbon, interesting atom here. As we look at carbon, we find it in its elemental form in a couple different spots. These allotropes of carbon, at least the two most common ones shown here, include graphite, which is really an arrangement of pure carbon atoms arranged in this hexagonal kind of a flattened lattice. Or, as you can see over here, diamonds. That's right, diamonds are pure carbon, arranged simply in a different geometry than in the case of the graphite, now with a tetrahedral formation. But those carbon atoms all have something in common, and that is that the carbon atoms contain 6 protons. And yet, when we want to figure out how carbon atoms interact with other atoms, it's not the protons that we really focus on, it's the electrons. And a neutral carbon atom happens to have 6 protons and 6 electrons. But the reactivity of that carbon with other atoms really hinges on the outermost electrons, or what we call our valence electrons. If you take a carbon atom and you were to draw those outermost electrons, we find that it has 1, 2, skip these few in the middle, 3, 4 outer electrons, whereas maybe you've drawn in previous Lewis dot structures a symbol like this: carbon with 4 outermost electrons. Well, what does that mean? What it means is that carbon is most stable when it has bonds that allow it to share those electrons with other electrons in order to obtain what we call an octet, or 8 outermost electrons. Atoms on the periodic table that have 8 electrons in their outermost shell are shown here. These are our noble gases that are noble because they're happy. Look at that. They've got a little smiley face. They've got 8 outer electrons. And carbon. Look at carbon. It's sad. Look at that. It wants more. How can it get more? It can bond. And so the different kinds of bonds that you've perhaps learned about, ionic bonds, or the donating or receiving of electrons, or covalent bonds, the sharing of electrons, are possibilities. In this case here, what we find is that carbon wants to bond through covalent bonds, or the sharing of electrons. And as it bonds through covalent bonds, what this really indicates is that carbon had one outermost electron here, 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 and here. But then other atoms could come and bring along their electrons, and in the end can result in there being 8 total electrons around carbon. Turn that frown upside down, carbon. It's now a happy little atom, and it's in good shape. Well, as we look at the structure then of carbon and how it can bond, we'll be looking today at a number of different atoms that find their way to bonding to a carbon atom. Here you see our carbon atom right here with its 4 outermost electrons, or 4 valence electrons. And we see accompanying that carbon atom, hydrogen atoms, and 4 of them. This is the molecule that we call methane, the simplest organic compound. And again, organic simply means there is a carbon atom that's involved in it. Well, you'll notice in this molecule that there is a bond between hydrogen and carbon, and the bond exists because hydrogen had a single electron, and now that that hydrogen brings its single electron to each of these bonding sites, we can share the electron pairs, and that's where we see the bond shown here. And so in this case, you see the ball and stick model that we like to call it, of a methane molecule, or CH4, as we would write the molecular formula. In addition to representing it with the ball and stick, we could see it represented with the space-filling model, which shows the carbon atom followed with the hydrogen atoms here in white. Or we could even represent it with the structural formula shown here, a 2-dimensional formula that can be helpful for just identifying numbers of atoms and general configuration. Once again, in either case, though, we're dealing with organic compounds, compounds that show the carbon present. Other representations of organic compounds will include not just the methane molecule shown here, but we can add on additional carbons. And in this case, you see a very simple molecule called ethane, where now instead of a single carbon, we've added 2 carbons. And we've filled in the outermost parts with hydrogens, so that that carbon now has, again, every line has 2 electrons being shared. 2, 4, 6, 8 electrons, making it a happy atom. This carbon atom has 2, 4, 6, 8 electrons, making it happy. And hydrogens likewise are content because their outermost shell, which can have 2 electrons, are filled with the 2 that each hydrogen is sharing. We also can see double bonds or triple bonds in the case of cyanide, for example, show up. And in those cases, that's just the most stable configuration for those specific molecules, in this case, ethene. And you'll notice some differences in naming if we have single bonds versus double bonds involved. We will change the ending to these. If you're interested more in this, organic chemistry is going to be a great option for you. Well, in terms of hydrocarbon diversity, if we just stick with hydrogens coming off of our carbons, we find that beyond just the straight up adding additional carbons in a linear fashion, we can also have branches that occur. Take butane, for example. It has 4 carbons in a branch. That butane with 4 carbons can also be written, though, and can also be present in the form of an isobutane molecule. Not an identical molecule, but rather there's a branch, still 4 carbons, but it's branched. We can have double bonds that can intervene, and those double bonds, as they intervene, as is shown here, will change the structure as well, will change the geometry of the molecule in terms of where each atom is located. We can even have rings like you can see in the cyclohexane or the benzene. Once again, if you see that ene, it's referring to now there's double bonds present, whereas that ane only has single bonds present. In either case, though, I want you to recognize this fundamental understanding, that is that structure of molecules influences their function and their properties. An absolutely essential understanding of all of AP biology, that structure influences and affects function. And we see it happening here at the molecular level. Well, where do we see hydrocarbon chains in our body? Hydrocarbons, to be honest, are fuel sources largely. We could find hydrocarbons in the form of oils and gases. We find hydrocarbons in places like our cell membranes. If you were to recall your general biology course and the study of cell membranes, here you see a cell membrane comprised of these heads that are attached to tails, a generalized molecule shown here of a phospholipid. And the phospholipid is named because of the phosphate head shown here, which is comprised of a phosphate group, as well as this other portion shown here. But then we are looking at the hydrocarbon chains that comprise the fatty acid tails. And these hydrocarbon chains are just lengthy linear portions of carbons that are tacked on to one another and that have hydrogens to fulfill their octet. Notice here how we have hydrocarbon chains with a little kink in the configuration because of the double bond. Again, single, double, triple bond that changes the geometry of the molecule and changes the bond angles. But one great example of how we see hydrocarbons in the body. Speaking of hydrocarbons, here you see a table showing a number of different patterns in terms of building the complexity of our hydrocarbon chains. Take a moment to look at that and identify what one pattern you can what one pattern you see in the layout of this table. All right, hopefully to this point you've identified here we've got a single carbon, 2, 3, 4, good. So we're increasing in our complexity as we move down, both over on this side as well as over here, 6, 7, 8, 9, 10. Complexity increases, good. In addition to that though, we can see how in the actual name of it, you might recognize some of the prefixes and how they relate. Hex, as in a hexose or a hexane or hexagon, we're dealing with 6. Hepta, 7, oct, 8. That's the number of carbons that we're talking about. Very good. And so as we increase in our complexity, we change the naming system as well. In fact, if I were to give you, using the same format here, simple unbranched alkane or a hydrocarbon that had a total of 12 carbons, how many hydrogens would you predict there to be? To do that, you got to understand the formula here. And so if we have n amount of carbons, what formula can you deduce from what you're seeing right here? All right, I think you're hopefully getting there. To solve this, we can take each one of these and identify that it's not just C to the N, H to the N. It's not C9H9, but rather it's at least double. What we see happening is that C to the N, H to the 2N plus 2. Case in point, C to the N, that would be C to the 1. H to the 2N would be 2 plus 2 would be 4. There you go. It works for all of these. So a simple formula that you can use, and if we apply that back to here, if you have 12 carbons, how many hydrogens should you have? H to the 2N would be 24. Add 2 more, 26. Booyah, very good. Well, one more thing stands out that I want to highlight, and that's this term isomer. Here you see isomers, whatever the heck that is. We've only got a single isomer for each of these simple compounds, but then we start growing in our numbers of isomers just as we grow in our complexity. So what are isomers? Well, let's take this molecule. If you count your carbons, 1, 2, 3, 4, and 5. This is a pentane hydrocarbon. And let's consider how many different arrangements we could have where we take the last carbon, and instead of adding it off of the fourth one, we stick it somewhere else. Where else could you put it? Well, as it turns out, if we draw this structure again, except maybe put that last carbon off of this carbon, how would that change things, right? Now, this carbon, if we were to stick this on the top of it, would have 1, 2, 3, 4, 5 bonds coming off. It would really have to change things, wouldn't it? But that's exactly what can happen. And as it happens, it ends up maintaining the same overall formula. Notice here for our structure of pentane, how we have 1, 2, 3, 4, 5 carbons. And again, if you were to count your hydrogens, C to the N, H to the 2N plus 2 as C5H12. Does that change when we change the configuration as we've done right here? 1, 2, 3, 4, 5 carbons. How many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Same formula, C5H12. Well, that's where the term isomer comes in. Isomers are strictly molecules that end up having the same chemical formula with varying structural formulas. Now take a moment and consider what other possible isomer can exist for pentane. Where else could you branch off besides off of that second carbon? Did you get it? That's exactly right. What if we go off of the middle carbon and we make two branches off of there? Anytime you see this designation, this just means a bond coming out towards you, and this means a bond going out away from you. It's an attempt to three-dimensionalize the structure. And so notice what's happening here. We have changes in the numbers of branches that we have. And that just as we increase in the branching, look what else happens. Do you notice this trend? Melting point increases. Boiling point decreases. And finally down below, density decreases. The theme holds true. You change the structure, you change the property. Such is the case with our structural isomers. Among the other isomers that we see, we can have isomers that vary in the geometry. For example, here you see a double bond between two carbon atoms. They are both happy atoms because, after all, remember, we have two electrons here. 2, 4, 6, and 8. That's a happy atom. The same with over here, happy atoms. They fulfill their octet. But what we identify here is these both share the same chemical formula. Same numbers of carbons, 1, 2, 3, 4 carbons, so C4. And now if we look at our numbers of hydrogens, 3, 4, 5, 6, 7, 8, H8. Both have the exact same chemical formula, but something's different about them. What is it? Well, here, if you were to draw a plane at the double bond, you can identify how your two functional groups or methyl groups are both on the same side of that double bond. And when that occurs, we refer to this as the cis configuration of that isomer. In contrast, if you go over here, notice if you were to draw a plane once again along that double bond, we see how our functional groups of the methyl, subunit here and subunit here, are on opposite sides. They are across from one another. Well, the Latin root for across is trans. And so this is the trans configuration of that isomer. Once again, isomer, molecules with the same chemical formula, with different structural formulas though, just as you can see here for this molecule. A great example of those isomers there, including the cis and the trans, is a specific molecule that you and I have in our eyes, really, in the rods and cones of our eyes. There is a molecule called retinol that will only absorb light at a specific wavelength. And upon absorbing light, leads to a signal transduction pathway or a cascading effect that ends up triggering a signal to be sent to your brain that says, boom, you've got light that you're detecting. Well, that all is initiated when this location of a double bond in the retinol molecule has a conformational shift in the arrangement of the downstream or the distal portion of the molecule away from this big ring over here into a trans configuration now shown here. Previous to that, notice if you were to look at this larger group and where it is on that double bond side relative to this one, they're all the same. That's why you get the cis configuration. But over here, after light's absorbed, it kicks this portion of it up. And now we have, if you compare it to the double bond, and again draw a plane right here, they're on opposite sides, this larger group and this larger group, making it the trans configuration. Big deal. This doesn't happen, you're not detecting that light. One of the most intriguing isomers that I like to present to my students has to do with this molecule right here, thalidomide. Thalidomide in the 60s was a drug that was prescribed to pregnant women to help them combat morning sickness. Not only that, it was used as an antidepressant, and it seemed to work quite well. Unfortunately, we discovered there were some severe effects of its use in kids who were born out of the pregnant woman who had been taking thalidomide to help to reduce morning sickness. Strange deformities, severe malformations of limbs particularly, Here you can see polydactyl showing up in extreme numbers of digits on the toes. In other cases, lack of arms altogether. As you can see here, Tony Mendoza, a famous Nicaraguan American singer and songwriter and guitarist who plays the guitar with his feet. What was going on with this? Well, it was discovered that the thalidomide that was administered and prescribed contained isomers, in this case called enantiomers. And the enantiomers were isomers that, man, they looked almost identical to one another. Can you pick out the difference from this molecule to this molecule? Do you see it? Right here in the middle of both of those diagrams, you see the hydrogen, you see the nitrogen, but there's only one difference. The nitrogen in this case is coming out toward us, and in this case it's going away from us. It's as though there's a mirror image, essentially, as though this molecule were to be reflected, and you see its mirror image right there. Almost as though you look at a left hand and you look at a right hand, and you see, well, they're not identical, but they're like a mirror image of one another. They're not the same, though. And what we found was that this isomer here was effective in reducing morning sickness and was an effective antidepressant. And this isomer was a mutagen. It had mutagenic effects, which led to those deformations. If you still aren't convinced about it, take this. We'll simplify this right now by focusing on this carbon atom right here, and we'll make it front and center. And then we'll take that and we'll call it these different R groups coming off of it. We've got an R1, R2, R3, R4. And now if you reflect that or make a mirror image of it, this plane here represents kind of a mirror, and you're to look at the mirror image on this side. Are those two really identical? If you have not convinced yourself yet that they are, or that they aren't, take a moment and try to flip this around in your mind, three-dimensionalize it by spinning it kind of on its axis to see if you match it up. And what do you see? Even if you spin it, they're not the same. So these enantiomers relate to these mirror images of isomers that, while they have the exact same chemical formula, their structures are just off enough so as to render their function, in some cases, totally useless. In other cases, rather than being ineffective, they cause much, much harm. Well, beyond hydrogen atoms that can certainly stick off of our carbon chains, just like you see here, once again, one carbon here, and now we've got our hydrogen sticking off. In this case, you have an ethane molecule. What happens when we substitute for the hydrogen other atoms, like an oxygen shown here, which is then attached to an H, or in simplified terms here, just an OH group, what we like to call a hydroxyl group? Does that really change the molecule much? Interestingly, it changes it a lot. Whereas we call this one ethane, anytime you stick this hydroxyl, or really an alcohol group off of it, you change the name of it, for one. This is now considered ethanol. And the result is changing a gas, which this will be, into a liquid. Ethanol. If you're not familiar with ethanol, ethanol is the primary alcohol in drinking alcohol. It is going from now a non-polar molecule to a polar molecule. So it changed its behavior entirely, all because we added a new functional group to one of those carbons. Well, functional groups are a big deal, and that's what you want to spend some time reviewing. Here you see several functional groups presented, the major functional groups you'll be responsible for learning. And as you look at the various functional groups and you memorize really their structures here, you want to be able to identify how changing the functional group changes the function of the molecule, changes the properties of the molecule. Such properties as in solubility, such properties as in reactivity, as well as even pH. You mess with the functional group and you can totally affect the rest of the molecule in its behavior. And so I hope this is a good introduction for you in learning about various organic compounds, carbon-based compounds, how they're built, how they're structured, and how shape and form and structure influences function.